Assalamualaikum and hi everyone. So before this, I have sent to you guys the introduction video on the Fourier series. Okay, so if you have listened to that video, you might notice that none of my explanation involve the differential equation. Okay, I haven't talked about differential equation. Okay, but then yet somehow this topic, okay, is commonly listed in most differential equation courses. Okay, so actually what I didn't mention earlier is that the important reason to learn the Fourier series in our context, okay, is basically to help us in solving the partial differential equation, which is the topic that we are going to learn in the next chapter, the last one. Right? So basically, in this chapter, chapter 4, no differential involved. Okay, but later on we are going to apply the Fourier series in chapter 5. Okay, so this is like the introduction part. So later on we are going to apply, okay, to in chapter 5. All right. So before we go to the finding the Fourier series, which is 4.3, okay, in your lecture notes, okay. So let us start with the three important things, okay, that you need to know first, okay, before we can compute the Fourier series. Okay, so they are the 4.1 here, the periodic function, and then the even function, and then the odd function. Okay, so we want to know what is the periodic function, how do we find the periodic, okay, how do we find the period of the periodic function, and what is the even and odd function, how do you recognize, how to prove, okay, and what are the properties of even and odd function. And then after that, only then we can proceed with the Fourier series. Okay, so a function ft is called a periodic function with period of t if it satisfies the rule here. Okay, so this one here should be the small f, not the capital F. Okay, because we are using the small f over here. So ft plus capital T equals ft. Okay, so it means that if we can show this equivalent, okay, things here, then ft is called a periodic. Otherwise, this is not a periodic function. Okay, so now first of all, we need to understand that the Fourier series, okay, as I explained before in the earlier video, the Fourier series is an expansion, okay, expansion of a function, of a given function in terms of sine and cosine. Okay, so the keyword is the expansion. So when we expand, okay, so basically the shape of the graph, okay, the shape of the initial graph will be repeated. Okay, so the repeated process over there explains the periodic. Okay, periodic is something that repeats itself. Okay, over time, or when you expand your x-axis. Okay, so that's why we need to know the periodic, and you need to understand that the Fourier series works on the periodic function only. Okay, otherwise we cannot get the Fourier series. So look at the example here. Show that fx, you know, the variable is in terms of x, not in terms of t. So show that fx equals cos 2 pi x is a periodic function. Okay, and then identify or determine its period. Okay, and then another thing, the period value, okay, is always a positive integer. Okay, start from 1. Okay, so 1, 2, 3, 4, 5, and so on and so forth. Okay, so it cannot be 1.5 or it cannot be negative 1.5. Okay, so it's just because we are talking about the periodic. Okay, so we want to know how many period. Okay, so it should be in terms of positive integer. All right. Okay, so back to the problem here. To show that f(x) equals cos 2 pi x is a periodic function. Okay, so you have a bit of part of the solution here. So since f(x) is cos 2 pi x, then we want to show f(x) plus capital T will goes back to the ft or not, or f(x) or not. Okay, so f(x) plus capital T, so basically we just substitute x with the x plus capital T. Okay, so the x here now will be replaced with x plus T. Okay, so we have so it means that we are looking for, okay, so this one first. Okay, so basically we want to know with a little bit of manipulation. So we want to see whether, okay, the 2 pi x plus capital T here will go back to the cos 2 pi x or not. Okay, if we can deduce, okay, it is going back to the cos 2 pi x, then it is a periodic function. Otherwise, it's not. Okay, so we know that. So we need to start from 2 pi x plus t here. Okay, so we know cos 2 pi x plus t. Okay, by the identity of trigo, so it is actually in the form of cos a plus b. Okay, so if we expand, then we have cos 2 pi x, okay, cos 2 pi t, okay, minus sine 2 pi x sine 2 pi t. Okay, so if we look at the right hand side here, so it will be equal to cos 2 pi x, okay, if this part here is 1 and this part here is 0. Okay, because we want to show that this is a periodic. So it will be equal to cos 2 pi x if if the cos 2 pi t is 1 and cos 2 sine sine 2 pi t is 0. Okay, because basically we want to get rid of this part. Okay, we want to get rid of the sine. Okay, so sine 2 pi t must be equal to 0. Okay, otherwise we cannot get back the cos 2 pi x. Okay, so basically we are questioning ourselves, what is the possible value of t so that you can satisfy these two. Okay, so what is the value of t so that cos 2 pi t is 1? And then what is the value of t so that sine 2 pi t is always 0? Okay, so it is true. Okay, so this is true for t equals 1. Okay, it's possible because we have cos 2 pi, which is 1, and sine 2 pi is 0. And it is also true if t equals 2. So we have cos 4 pi, which is 1, and then cos sine 4 pi, which is 0. And it is also true if t equals 3. Even t equals 4, 5, and so on up to, positive infinity. Okay, so basically we have t equals 1, 2, 3, so on and so forth. All right, but the period, okay, is determined by the smallest value of t. Okay, so the smallest value of t, as you can see here, the smallest value of t is 1, which is known as fundamental. Okay, fundamental period. So therefore, f(x) equals cos 2 pi x is a periodic function. Okay, this is a periodic function because we can show that, okay, from here you finally get back the cos 2 pi x, okay, if you satisfy this condition. Okay, so the period, okay, once we know that it is periodic function, so we need to be able to identify what is its period. Okay, so in this case the fundamental or the smallest value of t is 1, so that is the period. The process of proving the periodic function is actually a process of determine whether there exists a value of t that satisfies two equations. Okay, so I'll give you another case. Okay, so sometimes you have when t equals 1, for example, it satisfies the first equation, but okay, it doesn't satisfy the second equation. In that case, okay, it is not a periodic. Okay, so basically we are looking for the value of t that satisfies both. Okay, because we want to make sure this part is 0 and this part is 1. Okay, if it only satisfies the first one, it means that the term here still remains. Okay, then we will not get back the cos 2 pi x. Okay, so I hope you understand that one. But in the exam, okay, you are not going to see this kind of question somehow. Okay, so this is just for you to understand or to be able to determine the period of a given function. It might be useful in some other courses later. All right. So you can try on your own for example 2 here, and you need to show, okay, that the period is 2 pi over 5. Okay, 4.2, even and odd function. So in this part, we want to know how do we identify whether the given function is an even or odd function. Okay, so we have the rule here, the mathematical rule here for the even and odd function. Okay, so the first one, fx is an even function if we satisfy this rule here. F negative x equals to fx, and then it is an odd function if we can show that f negative x equals to the negative of fx. Okay, so the first one, so it means that if this is your x, okay, so the f is here. Okay, so here, so it is even function if we can show that if we take for negative x, it is also equals to fx. So it means it is also here. Okay, so if we can show that, then it is even function. So based on the diagram that I've sketched here, so we know that geometrically, so what you have here, geometrically, the even function in terms of graph, it is symmetry about the y-axis. Okay, so you can see here, if you have a point here, it is also here. Okay, so it means you can see it is symmetry about the y-axis. Okay, but for the odd function, so we have here the odd function. So if this is your x, okay, and this is your fx. Okay, so it is odd function if we take for negative x. Okay, if f negative x equals to the negative of fx. So if this is your fx, then the negative to the f would be somewhere down here. So it's supposed to be here. So this is your negative f. Okay, so it's supposed to be here. So everything that you have here in the first quadrant will be reflected to the third quadrant. So in terms of diagram here, you can see it is symmetry about the origin. Okay, so here. So if so the conclusion, you can prove whether the given function is even and odd, okay, based on two approach. Okay, whether you want to use the mathematical rule here, or you can look by the diagram. Okay, so I would suggest if you know the shape of the graph, if it is easier to sketch the graph, then it is in most cases is easy to check the even and odd function. Okay, based on the diagram. But somehow, if the function quite complex, okay, then we might want to use this rule here. Okay, so that's how we determine or identify whether the given function is an even or an odd function. Okay, and then if none of 1 and 2, this one here, these two things here, if we do not satisfy the two rules here, then we conclude that the given function is neither even nor odd, meaning that in order to say that the given function is neither even nor odd, it means that we need to check for the even first. If it is not satisfy the even criteria, then we need to check for the odd. Okay, if still do not satisfies, then we conclude it is neither. Okay, neither even nor odd. Okay, look at this example 3 here. So maybe I just show to you guys only 2 examples. So the first one, show that fx equals x squared is determine whether it is even, odd, or neither. Okay, so for this one, since the function given is very common one, okay, in the sense that it is easily can be sketched. Okay, so it's just parabolic, yeah, or quadratic. So for 1, we might just want to sketch. Okay, so fx equals x squared is just like this. Okay, so this is f equals x squared. Okay, so we look at the property. Okay, property of even and odd function. So if it is symmetry about the y, then it is even function. So clearly from this diagram, okay, it is symmetry about y-axis. Okay, then f(x) is an even function. Okay, number 2, hx equals sine x. Okay, so hx equals sine x. So this one you can sketch the diagram as well. But let's say you do not know how to sketch the graph. You do not know what kind of the graph of sine x. Okay, so so for this one we'll try to use the rule. Okay, so we have hx equals sine x. So we want to see for negative x. Okay, so h negative x, meaning that we replace x with a negative x, and we try to deduce whether the sine negative x here will go back to the fx or go back to the negative fx. Okay, so that's determine whether it is even and odd, or do not go back to either one of them. Okay, so sine negative x. So sine negative x is actually can be written. So it is actually comes from 0 minus x, right? And then by the trigonometric identity, if we expand this one, okay, if we expand this one, we will eventually see that this is actually goes back to the negative sine x. Okay, so I just remark here by trigo. Okay, you might want to work out on the trigo here by the trigonometric identity. So just expand sine 0 cos x, okay, minus cos 0 sine x. So you will see eventually you end up with a negative sine x. So negative sine x is actually negative to the f to the in this case hx. Okay, so if we look at the rule here, so it is actually this one. Okay, so we have h negative x equal to the negative of hx. So it means that the function h that we have here is the odd function. Okay, so therefore the given function hx is an odd function. Okay, so that's two examples to check on the even or odd function. So again, two approach can be used by the diagram or by the rule. Okay, so I hope you clear on that. So you can try for 3 and 4. So number 3 should be the odd function, and number 4 is neither. Okay, neither odd nor even. All right. Now, we want to see the properties, okay, the properties of even and odd function. Okay, so we have 6 properties here. So suppose you have two functions, f1 and f2. Okay, so if f1 is even and f2 is also even, so when you add or subtract the two function, it will be even function. The result of the summation or subtraction will be the even. Okay, if it is both odd, then the result will be odd. Okay, so if one is even, the second one is odd, then the result will be neither. Okay, so you can see from these 6 properties here, so the odd function is like the dominant, okay, dominant term. So it's like the negative. So if you have, for example, even times even, it will be even. So it's like you have positive times positive, so the result will be positive. Okay, so if you have odd times odd, then the result will be even. So it's like you have negative times negative, so it is positive, right? Okay, so you can illustrate the even and odd, okay, just like what you have in the positive and negative. Okay, so same thing, if we have odd divided by odd, then the result will be even. Okay, so for this one, I'll show you a simple illustration, okay, on this one. So we want to see uh, the truth of this. Okay, how do we simulate this one? What it means by the odd times odd will be even. Okay, so in terms of graph, okay, so individually, so I take the example for this one. Individually, okay, if you have the first function is odd, then you know it's supposed to be symmetry about the origin. Okay, so the second function also odd, so it is symmetry about the origin. But when you multiply or divide these two functions, the result will be even. So the shape of the graph will be now symmetry about the y-axis. Okay, so we are going to see that, okay, in the simulation. Now, this module, which is the Desmos here, Desmos Online, you can try on your own later, Desmos Online. So this module demonstrates the properties of even and odd function. Okay, what we have previous. So let's say we have two functions, f1 and f2 be the even, and then another two, g1 and g2 are the odd function. Okay, so the example of even function, we know that x squared is an even, okay, just now, and cos x is also the even. So, okay, so we have f1 and f2 are the even, and then g1 and g2 are the odd function. Okay, so you can prove on your own x cubed is actually the odd function, and just now we see that sine x is actually the odd function. Okay, so we'll look at the first one. So even times even will be even. Okay, so let's see this one, f1 and f2, because we know, okay, f1 and f2 both are the even. Okay, x2, x squared and cos x. So if we multiply, so first of all, let us look at the individual graph. So this is the graph of x squared, and this is the graph of cos x. Okay, so now we want to see when we multiply f1 and f2, the result is even. So it means that the graph is still symmetry about the y-axis. Okay, so you can see the shape of the graph is symmetry about the y-axis. Okay, and then if we have even times odd, we know that the result will be odd. Okay, so individually, the even is symmetry about the y, odd is symmetry about the origin. Okay, so we multiply F2 and G1. Okay, and we can see the result is odd. Odd means it is symmetry about the origin. Okay, so what if you have a point here, you also have a point somewhere here. Okay, so it is symmetry about the origin. So if it is symmetry about the y-axis, then this line here is supposed to be here, but it's not in this case. Okay, so that's the even times odd will be odd. Okay, odd and odd will be even. Okay, so this one, odd and odd will be even. So individually, G1 and G2. So this is G1. Okay, it is symmetry about the origin, and G2 is also G2 is symmetry about the origin as well. Okay, and then if we multiply G1 and G2, okay, so we can see now it is symmetry about the y-axis because it's already changed. Okay, odd times odd becomes the even. When it's even, the graph should be symmetry about the y-axis. Okay, so that's the illustration or the demonstration of the properties of even and odd function. Okay, so we'll go back to our lecture notes. All right, now let us see the integral properties. Okay, the integral properties of even and odd function. This is very important because this is very much related to the Fourier series that we are going to see later on. Okay, so the first one, look at the even function first. Okay, so if we have the even function, okay, so suppose we have f(x), which is the even function, then the integral from negative L to L, okay, any value as long as it is negative L to L, okay, if your L is 1, meaning that your integral is from negative 1 to 1, okay. So the integral of the function f(x) from negative L to L dx is equal to the 2 times the integral from 0 to L f(x) dx. Okay, so what it means by this equation here is that if we want to integrate the even function from negative L to L, okay, so it is equivalent to the finding the integral only half of the side, okay, meaning that we have the integral from 0 to 1, but we need to multiply with the 2. Okay, so now look at the explanation in terms of diagram. Okay, so take the example, the even function f(x) equals x squared. So we know, okay, x squared is the even function. Now, okay, let's say we want to integrate x squared from negative 2 to 2. Okay, so this is the graph. So this is the graph of x squared. Now we want to integrate from negative 2 to 2. Okay, so when we do the integration, so basically we get the area under the curve. Okay, so the shaded part here is basically the result of your integral. Okay, so the integration at the left hand side here is equal to the, okay, the integration of half part. Okay, so we take from 0 to 2, but then we multiply with the 2. So we will get the whole part again. Okay, so the reason why we need to know this, because it is easier, okay, to solve the integral if we have the limit 0. Okay, because we know that, okay, along the process we need to substitute x equal to 0. So it is easier to do that rather than get to compute to substitute x equals negative 2. Okay, especially when the f(x) here is quite a long expression. Okay, so this is only true if f(x) is the even function. Okay, this is only true if f(x) is the even function and the limits of the integral is from negative L to L. Okay, meaning that if we have, okay, so suppose the integral is from negative 1 to 2, then this is not true. Okay, this is true if we have negative 2 to 2, okay, or in general negative L to L, because we are basically can see here the two parts, okay, the left part and the right part is basically the same in terms of the area. They are the same. Okay, so that's why we can only compute on the half part, but we need to multiply with the 2. Okay, so this is the property of the even function. All right. And then the integral property of the odd function. Okay, so this is the best part. Okay, the integral of the odd function from negative L to L is straight away 0. Okay, so meaning that if you know, so later on, if you know that your fi is the odd function and somehow you encounter the integral from negative 2 to 2, for example, then you don't need to compute that. You don't need to do the integral. You can straight away write it is equal to 0. Okay, so look at the justification here in terms of diagram. All right, so take the example fi is equal to the sine x, which is the odd function. Okay, so now we want to compute from negative pi over 2 to pi over 2. So in terms of diagram, so we have from here to here. Okay, so we know that the sine x, the odd function is symmetry about the origin. Okay, so if we solve the integral, okay, so mean that at the left part it is from negative pi over 2 to 0, and then the second part is from 0 to pi over 2. Okay, so if we solve the integral at the left part here, okay, most likely we will get the negative value, and at the right part here we'll get the positive value. Then when we add up, it will be equal to 0. Okay, so for example, the result of the left part here is negative 2. At the right part is supposed to be positive 2. So when you add up, it will be 0. Okay, so that's the property of the odd function. Okay, again, this is only true if fi is odd function plus the integral is the limit of the integral from negative L to L. Okay, if you see the integral is, for example, 0 to 1, then it is not always equal to 0. Okay, this is only true if the limit of the integral of the odd function is from negative L to L. Okay, so I hope you're clear on that. Okay, so it is important to understand, okay, these properties of even and odd, okay, before we can proceed to the next section. All right, which is the Fourier series. Okay, so again, for the example illustration, so suppose our fi is an even, and then in the integral we have fx times sine nx. So we know sine is odd function. So since this is even, okay, so we have now even times odd. So we know from the previous discussion, when you have even times odd, the result of this multiplication will be the odd. So the overall, so the whole thing in this integral will be odd. So if you integrate the odd function from negative L to L, it will be 0. So it will go back to this property. Okay? So similarly, if you have fx times the cos, so since fx is the even, so even times even, so the whole thing here will be even, meaning that now we have the integral of the even function from negative L to L. So we can write it is equal to the integral from 0 to L. We take the half part. Okay, so it is easier to take the positive part. Okay, but if you prefer to take the negative part, then it's okay. Then it is also can be written as the integral from negative L to 0. You can do that as well, as long as you take only one part. But we need to have 2 in the front because we have to multiply with the 2 to get back the whole part. Okay, So and then if fi is not odd, okay, so now this fi is odd, you multiply with the sign which is odd, so the whole thing here will be even. So when you integrate the even function from negative L to L, then it goes back to the first property of the even function. Okay, so it is equal to the 2 times the integral from 0 to L. Okay, and for this one, if fs is the odd times the even, so the whole thing will be odd. So the integral of odd function from negative L to L will be 0. Okay, so in the exam, normally students wish to get the odd function. Okay, because they know whenever they have the odd function, and then the integral will be straight away 0. No need to compute. Okay.